Right, you've made it to part 3 of this very long Algebra 2 marathon of problems. We're going to start back up. Get your notebook, pen, pencil, anything you want to write with is fine. Let's see. Here we're going to simplify, so we're going to use some rules of exponents. When you see exponents like this, you can do two things. You can either distribute the power into every single place where an exponent would be. But what we can do in this case is we can simplify the inside. So whenever you can simplify from the inside out, that's really the ideal method here. And to simplify, if we're dividing any terms with the same base, you just subtract their exponents. Also, good to know is that any negative exponents are going to send an expression to the bottom with a positive exponent. And if there's a negative exponent in the bottom, that's going to put it up into the top with a positive exponent. So we can also go ahead and sort of shift our negative exponent terms to the other side of the fraction. So this is going to get moved down. We're going to have y10 down there, yeah? This is going to get moved up. So we're going to have z8 as a total, because 2 and 6. And then between these two, whenever we're dividing, you subtract your exponents. So this has a 1, even though it's not really there. And that's going to leave us with x cubed on top. Okay. Now, again, you could distribute the -2 to everything and make all of the exponents negative, or we can just use the negative exponent property, which is to flip this and now make the exponent positive. So we're just taking the whole parentheses like it's a whole box, and we're flipping the box. And now you can go ahead and distribute by multiplying the powers. So this is y20 over x to the 6, z to the 16. Okay, this would be simplified as much as possible. All right, good. Let's keep it moving. Here we have plenty of exponents to deal with. So just do things carefully here. You see 3 little packets, 3 boxes. We have to open up the boxes. Let's open up the top box. 4x squared times 4x squared times 4x squared. That's 4 cubed, which is 64. And then x squared cubed, that's 2 times the 3, will give us x to the 6. And here we have x cubed cubed, so multiply those powers, x to the 9. I'll combine them in a minute, but I see that I'm going to cancel stuff on the bottom anyways. On the bottom, that's 2x4 times 2x4, which is 4x8. And you can see we can cancel most of these. 8 of these on the bottom cancel with 8 of these, leaving us with just x. And also we can reduce the 64 with the 4, leaving us with 16. All right, very easy. So 16x to the 7, because the 6, and we still have 1 here. Very simple enough. All right, let's continue simplifying expressions. It's going to be a little bit tough to see, so just a moment. Hope you're digging the tranquil music today. X to the -9, y to the 5, to the -1, and we have 2 to the -1, x to the -4, y, and this whole packet, this whole box, is squared. I'm not sure if that made it better or worse, to be honest, but let's get started with the insides here. We have x to the -9, so that's going to go on the bottom, and we have y to the 5, that's going to go on top. And this is to the -1 power. Next, we have 1 over 2, and what else? X to the -4. Both of these are going down into the basement. 2 and x to the 4. And then on the top, what do we have? We just have the y. And this is squared. Now, before we continue, let's finish this dealing with this negative power. So we just flip that. X9 over y5. And then this will be y squared over, make sure you're distributing to every single exponent, even this number 2, 4x to the 8. And so we can cancel some terms on top and on bottom. We have 8x's here to cancel again with 8 here, leaving us with just x. We have 2 y's here, and we have 5 y's here, leaving us with 3. And therefore, we just get x over 4y cubed. Okay, now these exercises are not exactly what you should expect to see much of in pre-calculus. Or calculus specifically. This is to get you competent with expressions working with powers. So in the future, it's not just going to be x to the minus 9, y to the 5. It's going to be x squared plus 3 to the minus 9, 2x minus 7 to the 5, that type of thing, okay? So just preparing you for what's ahead. We're working with simple objects right now that are just single variables, but soon they will become their own expressions. Okay, let's look at some fraction powers. All right, we have an interesting case here. And I'm going to rewrite this again just in case it's not incredibly clear. We have a to the negative 4, b to the 8, c to the 6th, over b to the 0, c squared, a to the minus 2, and all of this is to the negative 3 over 2. Okay, first let's deal with the common bases on top and bottom. Anything that's negative, move it to the other side. So this negative 4 is going to go down to the bottom, and it's going to join the negative 2. That's going to make a squared, right? We're subtracting negative 4. We're basically adding 4 to the bottom is what I should say. B to the 0, that's just 1, so it doesn't really do anything. We're left with b to the 8. And then what about the c's? We have 6 on top, and we have 2 on bottom, so we're going to be left with 4 of them on top. All right, now all of this is to the negative 3/2 power. As you noticed in the last problem, I really like to flip it. Oh, oops. I said one thing and did the opposite. I really like to flip it. So I'm going to flip this. Have it to the 3/2 power. Now you can multiply that. You can do it carefully. You can do 1/2 first to everything and then multiply by 3. You'll get a cubed. Then you'll get b to the 12th. And you'll get c to the 6th. Okay, so that's just some exponent work. Oh, I think we have a little more exponent work, yeah. Sorry again about the picture quality on some of these pictures. I didn't notice how bad it was. We have s to the minus 1, r to the minus 4, over s to the minus 2, r. This is all squared. Then we have times s squared, r to the minus 1, over s4, r squared. And this is all to the minus 2. Okay, so lots of s's, lots of r's. Let's deal with this one at a time. This one has more to move on the other side, so we're going to add 2 to the top, and we're going to add 4 r's to the bottom. So that's going to leave us with s1, or just s, over r5 squared. Okay. Here we have 2 s's on top and 4 s's on bottom, so we're going to cancel the 2 s's and be left with 2 on bottom. And then we're going to take this r, the negative 1, and we're going to add 1 to the bottom. So this is going to be r3, and just a 1 left there. But this is to the negative 2 power, so let's do what I like to do and flip that. I'm actually going to flip it this time when I say it. Over 1, you can write it over 1, or you can just write it not over 1. It means the same thing. And then here we're going to have s squared r10. Let's see what all that comes out to be. Well, here we have 3 r's on the top and 10 r's on the bottom. So we're going to cancel 3 r's. We have plenty to spare on the bottom. We have 7 left. So our result is s to the 4th over r to the 7th. All right, great. All right, let's keep it trucking. So we're just going to find the x-intercepts. This is usually not too bad of a process. It kind of just depends on how you group it. They're giving us this equation, which is a cubic equation. And so if we want to find the x-intercepts, remember that that means y is equal to 0, right? Okay. So here if we take out x squared, in fact, I think -1 is a good number to try here. Yeah, -1 is actually a great number to try here. Notice that if x equals -1, we're going to just end up with -1 cubed plus 3 minus 3 plus 1, so everything is going to balance out and cancel to 0. So knowing that x equals -1 is a valid x-intercept, we can use the division process. We can use synthetic division for this to figure out what the remaining factors are. And with those factors, we can find some more x-intercepts. The process for synthetic division is putting the coefficients of the big polynomial right here, and we're about to divide by x plus 1. So we drop this down, that's a 1, and multiply it by -1. Then add these, we get 2, multiply by -1. Add these, we get 1, and of course multiply by -1, we should get 0 as the remainder. This represents the remainder. Okay, so what we're left with here, interestingly enough, is x squared plus 2x. That's what these coefficients now stand for. Instead of being cubed, now the highest is squared. And if you notice, this is a perfect square trinomial. So really, this expression, in case you didn't recognize it, is simply x plus 1 cubed. And so the only x-intercept is x equals -1. Or I guess you can say -1 comma 0. So if we take a look at the graph, just to get a little bit of a glimpse, it's going to look something like this. It's going to cross through 0 there. It takes off. Actually, it crosses through 0, 1 as well. So there we go. That's a little more accurate. All right. Number 60. Given that y1 equals 100 x plus 1 cubed, y2 is x plus 1 to the 5th. Oh, this is great. For what values of x is y1 equal to y2? So they're basically telling you what to do, how to set it up. They're telling you y1 equals y2. So we set these equal to each other. But I want you to be careful, because it's very tempting when you're trying to solve to just like go cancel crazy and try to divide everything that you see on both sides. And subtracting or adding to cancel on both sides is fine, but if you're dividing out things with x, you could be losing some solutions. Here's the best way to go about this. Instead of just dividing both sides by x plus 1 cubed, which fortunately doesn't actually ruin the answer here, that's kind of a coincidence, but in some cases it could eliminate the answer here. Let's see. There we go. What we're going to do instead is we're going to move this thing which has a common factor. We're going to move it over. And then what we're going to do is we're going to factor. Like I said, it has a common factor. So we're going to say 0 equals x plus 1 cubed. And then what's left inside? We're going to have x plus 1 squared remaining minus 100. Okay, now we're getting somewhere, guys. This is in the format of a squared minus b squared. So this is going to be equal to x plus 1 cubed times a minus b times a plus b. Oops. And so if we kind of simplify those factors a little bit better. This would be x plus 1 cubed, x minus 9, x plus 11. If any one of these factors equals to 0, then we have an x value. It says for what value, parentheses s, what values of x. So we just set each of these factors equal to 0 according to the zero product property. This is going to be x equals negative 1. This one's going to be x equals 9. This one's going to be x equals negative 11. All right, there you have it. All right, now it's time to move on to, that really came out a little bit different. Oh, that's a different page. Okay. It's like, wow, that really came out weird. I might have to fix that next time. Okay, so given y equals absolute value of this fraction minus another fraction, for what value or values of x is y equal to 1? Well, let's simplify the inside of the absolute value first. This is simply going to require us to multiply the first fraction by 5 over 5. Oops, I mean 4 over 4. So what we're going to do here is we're going to need to multiply the first fraction by 4 over 4, and the other one by 5 over 5, which is going to end us up with the absolute value of 4x plus 4 minus 5x minus 5, and this is all over 20, right? So we're going to end up with the absolute value of negative x plus 9 over 20. And we're trying to figure out when this is equal to 1. So it's possible that the inside is genuinely equal to 1, and so the absolute value didn't really change it, just kept it as 1. So negative x plus 9 equals 20. In this case, negative x equals negative 29, so x equals 29. And it is possible that the inside is actually equal to negative 1, but it gets flipped by the absolute value. So it's possible that negative x plus 9 over 20 equals negative 1, which would mean negative x plus 9 equals negative 20. And therefore, did I screw that up in the last one? I did. This is negative x equals 11. So x equals negative 11. Because here we are, negative x equals negative 29. So I knew I'd done something wrong the first time. And so x equals positive 29. Those are your two x values. And you can check them. You can plug them in for yourself and see that it works. You'll get 1. Okay, great. Solve over the complex numbers. What this means is we might get some solutions which have I in it, some imaginary solutions. We might not, but we might. So let's take a look at this. We don't really like the negatives, huh? So we should divide the negative 2 out. That's going to leave us with z to the 4th plus 27z equals 0. Now remember when I said we don't want to divide by something on both sides? That's only when it has a variable, remember. If it doesn't have a variable, it's fine. It's just a constant number. So now we're able to factor out z, and we have z cubed plus 27. I see, Mr. Z. This is a cube sum, the sum of cubes, where we have a cubed plus b cubed. And the factorization of that is going to be a plus b, so z plus 3 times a squared, that's z squared, plus ab, that's 3 times z, plus b squared, which is plus 9. Now this is considered an irreducible quadratic. It will not factor. In fact, its values, its zeros, are complex numbers, and that's why it requests us to find the solutions over the complex numbers, because solving these is easy. We just have z equals 0, z equals negative 3. But for this, we have a quadratic on our hands, and it doesn't factor. We're going to have to use the quadratic formula. you'll see that we end up with a negative inside of the square root. So b squared minus 4 times 1 times 9, there's your negative, all over 2 times 1 gives us negative 3 plus or minus square root of negative 27, which is going to require us to call this I, negative 3 plus or minus 3 root 3 I over 2. So our other values are z equals negative 3 plus 3 root 3 all over 2, and also z equals negative 3 minus 3 root 3 all over 2. Those are all of our complex zeros. Makes sense that we got 4 of them, right? Because this is a degree 4 polynomial. So we had 4 values which are going to give zeros. 2 of them are complex. You would not see them on the actual graph, on the graph of the xy plane. Okay, let's take a crack at this one, 63. Wants us to find the equation of a line that's tangent to the circle x squared plus y squared equals 25. Equation of a tangent line, I'm going to instill this habit now. It's a great idea to write the point slope equation for an equation of the tangent line. And here's what that looks like. It's y minus the y value equals m, the slope, just as you normally think of it, times the quantity x minus the x value. Where these, the x value and y value, these are from the point of tangency. So the point where it's actually tangent. What is tangent? Let's remind you. A tangent to a circle, especially, a tangent just barely touches a graph. So if we have this circle x squared plus y squared equals 25, which happens to be a circle centered at the origin. Looks like I kind of drew that a little off. Let me move that. That's a little bit better. The tangent line would be one that just kind of sits on it and just, oops, that goes, see how that goes through it? That's not a tangent line. If I want it to be a tangent line, I need it to just kind of sit on top of the line, just barely touch it. Yeah. So something like that, that is a tangent line. What's special about a tangent line? Well, there's this important property of a tangent line when it comes to circles. The tangent line, which is just barely touching the curve, happens to be perpendicular to the radius at that point. So the radius is the distance from the center to any point on the circle. There's a radius, there's a radius, there's a radius. The radii, that's plural, are all the same length. This radius here is 5 because of the equation. This is r squared, the radius squared. Now, this tangent line is perpendicular to the radius. So what I can do is I can find the slope of this radius line, this segment, by using the point 2 comma square root of 21, and then I can find the opposite reciprocal in order to find the equation of this tangent line slope, because I want the tangent line slope ultimately. I don't really care about the slope of the radius segment, but I need it so that I can find the tangent slope, which is the opposite reciprocal. So let's find the slope of this line. It's pretty easy. The rise over the run is just rad 21 over 2. So for the tangent slope, in other words, m, the value of m that we're looking for, this is negative 2 over square root of 21. Okay? So here we're going to have negative 2 over square root of 21 times x minus square root, x minus 2. And over here we have y minus square root of 21. Now, your teacher might want you to simplify this. If you need to simplify it, you can just multiply the top and bottom by radical 21. And on the bottom, it will break the radical. On the top, it'll just put a radical on there. And if they need you to add the radical 21 on the other side, that's fine. But I really want you to get used to this format, because looking forward at calculus, a lot of times we're going to use this point slope format. Okay. Let's talk another equation of tangent line. The difference here is that the circle is not centered at the origin. right? It tells us where the tangent point is. So we can already write y minus 2 equals m times x plus 3, careful with that negative, minus a negative 3. We just need the slope. And in order to find the slope, we need that line segment, again, from the center to the tangent point. But this time, the circle is not centered at 0, 0, so we have to go find what that center is. We do that by completing the square. Take these x terms, cut your b value in half, this is your b value, and square it. So negative 1 squared is plus 1. That's what we need to add here to complete the square. Now take your y terms, y squared plus 4y, do the same thing, cut the b in 2 and square it. That's going to be 2 squared, which is 4. Let me put that in purple just so we know what we're doing with that. We are artificially adding these numbers. And then let's move the 27 on the other side. So equals 27. We have to counterbalance the equation. We've added stuff to the left side that's not fair to the right side. And we've added this stuff so that we can make these perfect squares. Why do we make these perfect squares? Well, that's because the equation for a circle is given by the equation x minus h squared plus y minus k squared equals r squared. And so this is giving us the center location of 1 comma negative 2. The radius is the square root of 32, but that actually doesn't matter. We don't need the radius length, right? We never used the radius length in this question. We just used the slope from the center to the tangent point. We're going to do the exact same thing without a diagram. So we want to connect the radius from 1, negative 2 to this point which was given negative 3, comma 2. So what's the slope there? We can just do like the y2 minus y1, careful with that negative, over x2 minus x1. So we have 4 over negative 4, which is negative 1. Now that's the radius slope. We can call it like the radial slope. We want the tangent slope, which is the opposite reciprocal. So the tangent slope is just going to be positive 1, because if you flip 1, it's still just 1. But if you make it opposite, it is going to be negative. Negative 1 over negative 1, basically, which is just 1. So the equation of our tangent line is y minus 2 equals 1, or don't even put it if you don't want to, 1 times x plus 3. And this one is pretty easy to get into the slope-intercept form. If you want to move that 2 over and have both formats, that's fine. You can say y equals x plus 5. All I mean is, like, don't break your neck over it, like in this problem with the radicals and stuff. Okay, let's test the equations for symmetry about the x-axis, the y-axis, the origin. How do we test that? Well, let's think about what symmetry is, and let's think about these lines. So first, the symmetry on the x-axis. What would that look like? Here's the x-axis. So if the x-axis were like a mirror, that means if there's anything on the top side, then it's also on the bottom side, right? X-axis symmetry, that's what that would mean. If it goes like this, then the mirror reflects it pretty much like that, okay? How do we test for that? The way we test for that is we make the y values opposite. So see all these points? They have the opposite y values to these points on the bottom. We make the y value opposite and see if we get the same x value. Now, some of these graphs you should be familiar with anyways. What do we call symmetry across the y-axis? It's the same idea, but the way that you check for that is you plug in the x and negative x to see if you have symmetry on this side. For example, a parabola. And for example, the parabola in part A. It's shifted upwards and it's a little skinnier, but it's still symmetric. It hasn't been shifted to the left or the right side. And lastly, the way that we test for origin symmetry, if it's reflected across the origin, so that means there's a point here, and there would also be a point like literally across here, that means that negative x, negative y is also present. So in other words, it's symmetric on the x-axis and the y-axis, both of them. Because if you think about it, if I flip this over the x-axis and then flip it over the y, well, there I am. Or vice versa, if I flip it over the y first and then I flip it over the x, I'm still at that same point. So let's just kind of walk through the tests for this. The thing that you'll most likely do every time, if you know the graphs, again, it's really helpful, you can tell. And if you know some other tricks, it's kind of helpful. But what you're going to want to do is you're going to want to plug in negative x and just simplify and work out the expression and see if you get the same thing as the y, the original, or not. In this case, negative x times negative x becomes positive. So yeah, we get the same thing as if we just had positive x, which means this has y-axis symmetry. We also call these functions even. If we check it for x-axis symmetry, well, it's pretty obviously not the exact same thing, right? If we were to say negative y equals 2x squared plus 7, and then solve for the y again, that means y equals negative 2x squared minus 7. Definitely very different from what we started with. So there's no x-axis symmetry. And of course, we know that this is a parabola, so like we know it doesn't have x-axis symmetry, right? It's like that. Okay, here's an interesting one. We're going to check for x-axis symmetry by plugging in negative y. If we plug in negative y, actually the first thing to plug in is usually easier is y-axis symmetry. Let's plug in negative x here to the fourth plus 1 over negative x cubed. Notice that in the top, the even power is going to turn that back into a positive x to the fourth, but the negative to an odd power is going to end up a negative on the bottom. And so this is the same thing as negative of what we started with. And that means this thing has origin symmetry, because that means that negative x gives us a negative y. Let's look at this one here. This is not a function. This is just a curve. So if we plug in negative x, 5 times negative x squared, this one becomes a positive. This one becomes a negative. So this is not the same. In fact, if you factor the negative out, see how now we have x cubed plus y squared? And so this will never be the same. Let's plug in negative y. If we do x cubed minus negative y squared equals 5x squared, this one does change to a positive, which is the original graph. So this one has x-axis symmetry. Okay, that was a nice little exercise. Here we go. We want to simplify this. This is square root of 2 minus square root of 8 plus square root of 18 all squared. You don't really want to write this out like this, trust me, or you don't want to work this out using like an extended, it's not even really FOIL because these are not binomials, this is 3 terms. You really don't want to multiply all that out. What you should want to do first is simplify these radical expressions. So this is square root of 2 minus 2 square root 2 plus 3 square root 2. And this is all squared. So simply we have all of this combined together with the minus 2 in consideration. 2 root 2 squared. This is 4 times 2. This is 8. Easy peasy, way easier than trying to work all that out and FOIL all that out and stuff. If point A, which is at 3, 4, is the midpoint of the segment connecting point B, 1, negative 2, to point C, which is at A, comma B, then what is A plus B? Okay, so we need to find what A and B are, but we need to find that so that we can add these together. 3, 4 is the midpoint. Here's the easiest way to do that. It's not going to be drawn on a perfect XY plane. I just know that it's in the middle. So we're going to put B over here, and we're going to put C over here, which has coordinates A, comma B. This has coordinates 1, comma negative 2. The simple question is, how do I take this x value and go to a 3? I'm going to just plus 2. And how do I take this negative 2 and go to a 4? Well, that's simply going to be a plus 6. And if this one is halfway there, you can do the same instructions, plus 2, plus 6, in order to get onto the other side, because you went halfway, which means you have to do the exact same motion again to go the second half. It's an identical path because you were going straight there. So if you're going straight somewhere and you're halfway there, you have to just do the same thing you did and you'll finish the second half. That's why it's called half. So that means this point is at 5, 10. And therefore the A and B, 5, 10, we add them together, 15. Nice. Very nice. Okay, let's talk about this. We have not brought this up about lines before. Two lines defined by the equations y equals 9 minus 2x, y equals 10 plus 4x, they are intersecting, and we want to figure which quadrant. So which one of the squares, which one of the corners? Well, how do we figure out where they even do this? If they intersect, this means same location. This means same x and y. So their x's are equal and their y's are equal. It's really useful that their y's are equal because we have the equation of the y, 9 minus 2x, must equal the equation of the y, 10 plus 4x. And here we see that we can really easily isolate this. Just add 2x, subtract the 10, and we have minus 1 equals 6x, so x equals negative 1 over 6. And then if you want to find the y value, because now we know the x value is negative, so we know it has to be somewhere in here, in the left 2 quadrants somewhere. Now we can plug in the y. Let's use the 10 plus 4x equation. I think that's a little bit better. 10 plus 4 times negative 1 over 6. Well, of course, that's going to be positive. You don't even have to bother calculating that. Right? We just know this is greater than 0. So this will be in the positive y quadrant, negative x quadrant. That's the second quadrant. Bam. Oh, okay. Speaking of some quadrants, does the point 4, 6, does it lie within the circle of x squared plus y squared equals 45? This is very interesting. It's a circle, right? Centered at 0, 0, right? And the radius is the square root of 45, which we can say is the square root of 9 times the square root of 5. That's just 3 times the square root of 5. And what we can do is we can say that is sort of the perimeter. That's the distance, right? It's the radius technically, but that creates this perimeter. And we're trying to find out if 4, 6 is inside of that boundary, inside of that fence, or if it's outside of that fence. Well, one way we can check is we can see the distance, because maybe 3 square root 5 is not obvious what its value is. But we can check 4, 6 and maybe check the distance by using the distance formula. And we will see if that distance is bigger or smaller than square root 45. I drew it kind of perfectly on the circle, but we don't really know exactly where it is. So we're just going to draw it not even centered there in the center. Just going to draw like this. 4, 6 is the point, right? X equals 4, y equals 6. There's the point. So this distance is going to be square root of 4 squared plus 6 squared, which is the square root of 16 plus 36, or the square root of 52. So that means the distance is further than the radius. That means this is like outside of the circle. Got it? Because the circle itself is every point that has this distance away, the radius, square root 45. So if we find the distance away and it's more than that, that means it's further out than the radius, which means it's outside of the circle. Okay, great. Back to these rational situations here where we're finding all real solutions. We have to exclude some values first. So let's go ahead and factor this. This is nicely going to factor to x minus 4, x plus 1. If you can't see it, it's a 5x on top. This is a 1. This is x minus 4. It's being subtracted. And this is 3 over x plus 1. Okay, so I see that the restricted values are the same for these two factors as for these two. That's good. So x equals negative 1 is restricted, and positive 4 is restricted. Okay, now let's go by multiplying everything, every fraction, by this. And we end up with 3 times, because the x plus 1's cancel, x minus 4, minus 1 times, because now the x minus 4's cancel, it's going to be x plus 1, equals 5x, because the whole denominator will cancel. Okay, this isn't bad. This is just a linear equation. 3x minus 12, negative x minus 1. Combine all your x's on one side. Let's move everything with x to the right side. So we have negative 13 equals 3x, and therefore x equals negative 13 over 3, which is fine. That's not restricted. It is kind of a funky value, but it's not restricted. In fact, it's so funky. Let's make sure that I did this correctly. Yeah, we add x, which gives us 6x, and subtract 3x, which gives us 3x. There's the negative 13. Yeah, looks good. Always good to take a moment sometimes to check your work. Make sure you did it right. Okay, this expression. Here we have a rational expression. We're multiplying rational expressions. Oh, that's a division, sorry. If it looks a little blurry, it is. This is k plus 7 over k minus 5 divided by k squared minus 49 over k squared minus 25. Remember that dividing by a fraction is the same as multiplying by its reciprocal. So on the top, we're going to multiply, by the way, and on the top, we're going to have this difference of squares, a squared minus b squared. So we're going to have a minus b, k minus 5, and a plus b, k plus 5. That got on the top because we flipped the fraction. Now this one is a difference of squares as well. We have a squared and b squared. So this is going to be k minus 7 and k plus 7, which nicely cancels with these factors. See, the k plus 7's cancel, the k minus 5's cancel. We end up with k plus 5 over k minus 7. Okay, that one was actually pretty easy. Here's another complex numbers. They use that phrase. They don't use it lightly. Solve over the complex numbers. So that means that there's going to be some I stuff involved. Let's rewrite these. This looks so weird to have a negative 2 exponent, 3 over y squared, minus 4 over y, plus 1 equals 0. Okay, so of course, that means y cannot equal 0. There would be a problem if y equals 0. But let's multiply everything by y squared. This would be 4y, and this would be y squared. So maybe I'll write it like this. And if you notice, that does factor. Y minus 3, y minus 1. I guess there's no I business here. Our solutions are simply y equals 3 and y equals 1. Easy. Here, number 73, find all real solutions. So here we have x plus 7 to the 3/2 power. We can't get to the x because of the exponent on the brackets or on the parentheses. But what we want to do is we want to do the cube root of both sides, and then we want to square both sides. When we take the cube root, that's the same thing as doing times a 1/3 power, and so 27 also to the 1/3 power. So here now we have x plus 7 to the 1/2 equals 3. That's the cube root of 27. And then we can square both sides. So here we have x plus 7 equals 9, which means x is 2. You can plug it in for yourself, and the left side will equal the right side. You plug in x equals 2. Now when you square both sides, you don't take a plus or minus. When you square root both sides to solve an equation, you do take plus or minus. And if you cube root both sides, you do not take plus or minus. I know that can be a little confusing. Oh, here's a pretty formidable problem. Find all real solutions. Okay. So if we have a square root, we're going to want to isolate the radical every time so that we can square both sides. In order to do that, we're going to add 1. And now when we square both sides, we're going to have to square this with FOIL, this binomial, x plus 1. Let's go ahead and do that. So what do we end up with there? We end up with 2x plus 5, because the radical breaks, is x squared plus 2x plus 1. Now that seems all fine and dandy and easy and solvable, but what you have to remember is that when we get x values at the end, since we're dealing with the square root, we can't have a negative in there. So 2x plus 5 needs to be greater than or equal to 0, which means 2x needs to be greater than or equal to negative 5, which means x needs to be greater than or equal to negative 5/2. So just keep that in mind when you solve this. Also keep in mind that when we get to the second step, before we did the squaring of both sides, we need to check our answers, because this square root cannot be equal to a negative. So those are just some things to consider when we're done solving this. Let's move things over. Minus 2x, minus 5. Oh, that 2x's cancel. And we end up with x squared minus 4, which of course is a very basic difference of squares. You should be super familiar with that one. X minus 2, x plus 2, which means x equals 2 and x equals negative 2. Now, neither of those are less than negative 5/2, which is good. They're both greater than or equal to negative 5/2, but we still need to check these. So if x equals 2, then we're going to get square root of 4 plus 5, that's just square root of 9, equals 2 plus 1, that's 3. Checks out. Seems legit. If we try x equals negative 2, we get square root of 1 equals negative 2 plus 1. That is not acceptable. If we get square root of 1 is negative 1. That is not the case. So the only valid solution here is x equals 2. And I won't say that it's always the negative values that don't work, but a lot of times just with sort of easy problems, that's how it ends up. So, maybe check the negatives first, but that doesn't mean you should expect them to always be extraneous solutions. And that also doesn't mean that positives can't ever be extraneous solutions. So, yeah. Okay, let's look at the endpoints of the line segment, A and B. Sketch the reflection of AB. I don't know that I want to sketch it necessarily, but I do want to translate the endpoints at least. So let's see, what are we looking at? Negative 2, negative 3 to 3, negative 1. Let's get zoomed in here. -2, -3. There we are, nice purple dot. And then 3, -1. Okay, I have an idea of this now. If I want to reflect this over the x-axis, what's going to happen? It's going to get reflected over this x-axis line, which means the y values are going to flip. All the y values are going to flip. So now we're going to have -2, +3, and 3, +1. That's pretty much all she wrote. You can see that it's flipped over. All right, let's flip it over the y-axis now, which means we're going to send it from the left side to the right side, or vice versa, which means we're going to flip the x value. So now that starting point of -2, -3 is going to be +2, -3. And that point 3, -1 is now going to be -3, -1. So you can see it kind of got flipped. The original one sort of goes through here, kind of like that, sort of. A little different, but a little more like that. All right, let's flip it over the origin now. If we flip it over the origin, we're going to basically flip it over the x and the y, so we're taking -x, -y. So now the first point A is going to be at +2, +3, because it flipped directly across that, and -3, +1. There we go. And lastly, we're going to flip it over the line y = x. And to do that one, we simply switch the x and the y. So let's draw the y = x line for reference. -2, -3 is going to switch to -3, -2. See, this point, which was originally below this line, is now reflected on the other side of the line. And then 3, -1 is now -1, 3. Wow, that's interesting. So there we have it. The original line again was something like this, and you'll notice that those lines would intersect if we continued them. Okay, so that's our reflection of these line segment points. Really good, really good. Oh, here we are working with absolute value again. Remember that absolute value stays the same if you're putting in a number that's not negative. If you put in a number that's negative, it's going to flip it to the opposite. So if y = x + 3, that means that y minus x = 3. And that means x minus y, which is -y minus x, equals -3. Which means that, because y minus x equals 3, obviously. But if we take the absolute value, that means this just equals 3 again. So those two absolute values together are simply 3 plus 3, but this one's a flipped 3, so it's like flipped 3, almost like it used to be a -3, but now it's +3, plus 3, because it was genuinely equal to 3, equals 6. Yeah, pretty easy. Okay, we'll finish up with this one here. Pretty easy last leg. Let's do a sprint. The slope of the line passing through these 2 points is equal to just a simple y2 minus y1 over x2 minus x1. Careful with the negative. Subtracting a negative is the same as adding. So this is going to be 3 over 5. Perfect. That's the slope. And I'll see you back with part 4 when we finish up this assignment. The problems are going to get tougher in the last leg.